On this worksheet, we're going to practice rearranging carbocations to form something that is more stable. The stability of the carbocations follows this trend. The methyl carbocations are the least stable. Primary is next, then secondary, and then tertiary. That's the most stable carbocation. A tertiary carbocation is just one that has 3 carbon-carbon bonds. Secondary is one that has 2 carbon-carbon bonds. A primary has 1 carbon-carbon bond, and a methyl carbocation would have 0 carbon-carbon bonds. And this is, kind of a really simple definition for primary, secondary, tertiary, but it's going to work for this worksheet. So I'm actually going to skip this first example because it's a little bit tricky to verbalize, and I'm going to start with the second one on here. When we're looking at carbocation rearrangements, we want to begin by focusing on the carbon atom that currently has the positive charge, which is this guy right here, and we want to classify it as methyl, primary, secondary, tertiary. This carbon has 1 carbon-carbon bond, which means that this guy right here is primary. And so that means our goal is to try to rearrange it to form something that is better than primary. So that would be either secondary or tertiary. In the rearrangement process, we're only allowed to move the positive charge, move the carbocation, to a carbon atom that is directly attached to its existing location. So that would mean that we would be allowed to move this positive charge into this position because this carbon atom is directly attached, but we would not be able to move it all the way out here on the other side because this carbon atom is not directly attached to where the positive charge is currently located. We wouldn't want to do that anyways, but our only option is to put it here. Before we decide that we should actually do this rearrangement, we have to ask ourselves, would this even make sense? If we put the positive charge on this carbon, would that improve the stability? Remember, we're trying to make it secondary or tertiary. So the carbon that we're considering for placement of the carbocation is this guy right here. Let's categorize that. That carbon atom has 2 carbon-carbon bonds, which means that it is a secondary carbon, which means that yes, if we moved that positive charge over onto this guy, we would be increasing the stability. So once we have that figured out, we know that we want the positive charge over here. If we're being asked to draw a mechanism, we need to figure out what we have to move, what we have to actually shift off of this carbon atom to make it possible for the positive charge to be positioned there. And typically what we're going to be shifting is a hydrogen. Like 95% of the time, that's what's moving. So we just have to make sure that there is a hydrogen atom on our target carbon, something that's available to actually shift over and take the place of the positive charge. Now this worksheet's not asking us to actually sketch out the mechanism, it just wants us to show the rearranged carbocation. So we're like not really needing to worry about that mechanistic step, but I'm going to draw that in here anyways. So let's practice with this one right here. Begin by identifying the carbon atom with the positive charge and classify it. What is that? That's a primary carbon because it has 1 carbon-carbon bond. Now let's consider possible sites for rearrangement. Remember, we can only rearrange to a carbon that is directly bonded to our existing carbocation, which means our only option is this position right here. We could not do a rearrangement on any of the other carbons in the ring because none of them are directly bonded to that carbocation. So once we've identified where we can go with it, we need to classify that carbon. That carbon is a tertiary. It's got 3 bonds, which means that this rearrangement does make sense. We want to just simply swap that positive charge into the tertiary position. Now what I'm describing here is, kind of like it's a pretty quick and simplified explanation of how we do this rearrangement. And so some people might be a little cranky about what I'm describing, but this is a strategy that's going to work for you. It's going to make it work. So here's our next example. Here's our carbocation, and we want to classify that guy. That guy is a secondary carbocation because it is bonded to 2 carbon atoms. When we're considering places where we could do the rearrangement, remember we can only rearrange to a carbon atom that is bonded directly to our existing carbocation. So that would be this position or this position right here. So we've got two choices. Let's categorize those. The one on the right is a tertiary carbon. The one on the left is a secondary carbon. The one on the right is bonded to 1, 2, 3 carbons. The one on the left is bonded to 2. So we've got two choices. We could move our positive charge over here, or we could move our positive charge over here. Our goal is to form something that is more stable, which means that we're trying to increase the stability. We're already a secondary carbocation. It would not make any sense for us to rearrange to form something that's exactly the same. So we're not going to see our rearrangement in this direction. Instead, we're going to see a rearrangement going this way. And then let's draw that out. That's going to look like this. See how easy this is? All right, so let's take a look at our next example. Here's our carbocation, and here are the carbon atoms that are directly attached. So those are the ones that are available to us. And let's classify all of them. From left to right, we have primary, we have secondary, and we have tertiary. Right now, our carbocation is on a secondary carbon. It is definitely not going to rearrange out to the end here to make a primary carbocation. That does not make sense because that is less stable than secondary. So we're going to see the rearrangement happening out here to the tertiary carbocation. That is going to give us this guy right here. Here's our next example. Here's the positive charge, and here are the carbon atoms attached to it. Let's classify them from left to right. We have a tertiary, a secondary, and a primary. The carbocation is currently on a secondary, so that means it's going to want to move on to the tertiary position. And that's going to give us this carbocation. And then down here, we have another example. Here's our positive charge. Here are the carbon atoms that are attached to it. Let's classify them from left to right. We have tertiary, we have secondary, we have primary. Let's shift that positive charge from the secondary to the tertiary. Now let's go back up to the one that I skipped. I said I just wanted to skip this one initially because it wasn't going to be as easy for me to verbalize. It's still pretty simple. So here's our positive charge, and this is the only carbon atom that we have available to do the shifting. Our carbocation is currently on a primary, and our adjacent carbon atom has 4 bonds to it. So that's not like one of our classifications here. That's like a quaternary carbon, because it's got 4 carbon-carbon bonds. Because it has four carbon-carbon bonds, that means it doesn't have any hydrogens on it, which means that we cannot shift a hydrogen atom, but we are able to shift methyl groups or whole entire alkyl groups when necessary. So for this one, we are going to get a shift. We are going to be moving, instead of a hydrogen atom, we're going to be moving one of the methyl groups over onto that positively charged carbon. So that's going to leave us with only one methyl group in that spot, carbon number 2, and we're also going to be adding an extra methyl group onto the end of the carbon chain. And what I'm going to do actually is, I think what I'm going to do is use a different color here, and I'm just going to kind of highlight that particular methyl group so you can see that it's actually been shifted. But this does leave us with a tertiary carbocation, which is more stable.